So this is the second lesson, completing the unit on limits. Still looking at the idea of a derivative and really introducing the idea of a derivative. And I start with a bunch of statements that are all equivalent. So first, the instantaneous rate of change. Imagine you're driving and you look at the speedometer. You look at how fast you're traveling. That your speed at any given time, that's your instantaneous rate of change. It's probably fluctuating, but at any instant that you look at your speedometer, that's the instantaneous rate of change of your car at that point. And that's sort of analogous to so much that we're doing in this course. That if you're driving again, that speed will surely change, and over a period of time, you have an average speed. But at any instant you look at your speedometer, that's the instantaneous rate of change of your velocity, of your distance, I should say, at that point. Well, the instantaneous rate of change for any function is equivalent to the slope of the tangent line at that point. And the slope in general is found by the change in y of the change in x. But the slope of at an instant is when that change in x, your run, is approaching 0. Because the slope between 2 points is the average change. And again, my analogy of driving, the average change would be, let's say it took you 2 hours to travel 200 kilometers. So your average speed was 100 kilometers. But your instantaneous change, your velocity at any given point is changing over those 2 hours. But the average is just a fairly simple calculation. So in this case, again, instantaneous rate of change, same as the slope of the tangent line at that point, same as the limit as x approaches 0 of slope, which is equivalent to this. If we think in function notation, which is what we worked with a lot last time, which using function notation, we call that f prime, which we also call the derivative. All of these things you see highlighted in yellow are equivalent. And this idea of instantaneous rate of change is fundamental to differential calculus. Again, a derivative is a measure of the instantaneous rate of change of anything. All right, so I have two problems. One, coming back to this, which we saw earlier in the course. I have a scatter plot here showing some data of how people's blood alcohol level changed over time after they ingested 2 drinks. And this is the scatter plot of their data. And I want us to imagine A of t representing the blood alcohol level as a function of time. And so I have a scatter plot here. So I want to imagine a function that somewhat kind of connects the dots here. So something like this. So I'm imagining this change. And this being y equals A of t, where t is time in hours, and A is the blood alcohol concentration. All right, so we've actually saw this earlier on the course, like I said. So I want to ask first, what is A prime at 0? Okay, estimate A prime, not A at 0, A prime at 0, and state the units. So that means the instantaneous slope of this at 0. So if I look at 0, I have to kind of visualize what the tangent line would look like, and it would look something like this. Some sort of fairly steep line. Actually, I probably drew that a little too steep. Let me grab a ruler here. Either way, I'm estimating, but I don't know. It's a little easier with a ruler. So maybe something like this. Okay, that's my estimate for what the tangent line looks like at 0. So what's the derivative at 0? Well, the derivative is the slope of this line. And so, for example, to find the slope, I can pick 2 points. And so if I look at these 2 points here, from here to here, the rise is 0.2. The run is, I got to look at units on my x-axis. This is 0.2 right here. That's about halfway, so about 0.2. So I would say my estimate for A prime at 0 would, again, the change in y over the change in x. Or in this case, about, like I said, the change in y about 0.2 divided by the change in x about 0.1, which is just 2. Now, what are the units? The units are, again, the change in y divided by the change in x. So the milligrams per milliliter per hour. Now, what's that the same as? That's the same as 2 milligrams per milliliter hours. That's it. That's my quick little estimate from the data here. It's definitely going up. The units, I'm sure about the units. The actual 2 is all based on my estimate of this little tangent line. But the idea is what, a prime at 0 means what it just found. It means the slope at that instant. All right? Similarly, estimate a prime at 2. So a prime at 2, here's 2. So let me imagine what the tangent line looks like at this point. I don't know, something like this. Oh, come back here. And let me find, to find the slope of that. So let me pick 2 points that seem fairly easy to visualize. How about there and, I don't know, there. So look at these 2 points. So a prime at 2, again, change in y over change in x. So for these 2 points, that change in y looks to be about 0.1. If I'm looking at this right, yeah, roughly 0.1. And the change in x here, this is 1.8, this is 2.6, so 0.8. And 0.1 divided by 0.8 is 1/8. But it's going down. My change in y is negative. Almost missed that. So negative 1/8. And again, the units are milligrams per milliliter hours. All right, so notice my derivative is, when the slope is going down, the derivative is negative. The slope is going up, the derivative is positive. Because again, the derivative is just a slope at some point. So what's quite often a very important derivative is when the derivative equals 0. So I want to estimate when a prime equals 0 and then state what this represents. And first, what does that mean when a prime equals 0? Well, that means when the slope of the when the slope of the function is 0. And a slope of 0 is a horizontal line. So think, when is this function not horizontal, but when would the tangent line be horizontal? If I look at my function, it's roughly about right here. At that point, the slope of the tangent line, so I'll draw an orange here, would be horizontal, somewhere around there. And so where is that? Again, I'm just kind of estimating. It's roughly halfway between 0 and 1, so at about 0.5. So roughly when t equals 0.5. So what does that represent? Well, this represents after 30 minutes when your blood alcohol level peaks, when the blood alcohol level is at its highest. That represents. It's when it changes from the blood alcohol level going up to going down, which this idea of where the derivative equals 0 is usually a very important point for any function. It's where there's, in this case, the peak, which is usually an important thing to pay attention to for a function. And so in this case, again, this is when the blood alcohol level is at its highest. I'll say it's at its peak. All right, so notice for these 3 questions here, no calculations really, aside from a little bit of estimating some slope. It's about understanding what the derivative means. And we never want to lose sight of that. This course is essentially about a derivative and working with derivatives. All right, so now let's look at a function in which I actually want to calculate the derivative. And so I have the equation of y equals x squared. Sorry, not y equals x squared, x to the negative 2. Which, keep in mind, is the same as 1 over x squared. And I'll write that down right here as well. That's it. I want to find the derivative at a. Which really means I want to find the derivative just at any number of my choice. And so how do I find the derivative at a? Well, we saw this last time. To find the derivative at any given point, a is just some number. I want to find the limit as h approaches 0 of this. And again, we call this the definition of the derivative. And again, if a was like a set number, if I asked for the derivative at 2, there'd be a 2 where those a's are. I could just leave a as x as well, the derivative at x. X can be some number. Again, it's all kind of the same idea. That's it. Let's evaluate this limit, and let's start by actually, substituting what the actual function is. So f at a plus h will be 1 over a plus h all squared. Minus f at a is just 1 over a squared all over h. OK, well, at this point, a few things. Dividing by h, I'm going to write as multiplying by 1 over h, and I want to find a common denominator for the numerator. So for the numerator, my common denominator would be a squared times a plus h squared. And my denominators would be a squared minus a plus h all squared. And again, instead of showing this all being divided by h, I'll have it multiplied by 1 over h. All right, now let me kind of expand and simplify, at least definitely the numerator. The denominator is actually all nicely factored out. If I look at my denominator, I have factors of a squared times a plus h squared. Sorry, I wrote this down wrong. I realized right here. This should be, there we go. So my denominator are a series of factors, a squared times a plus h squared times h. I like factors. The numerator is not factored, so let me, again, expand and simplify. So I get a squared minus, and again, keep in mind this part right here is the same as a squared plus 2ah plus h squared. But I'm subtracting all of this. So while I could put brackets around this, I'm just going to change the signs. There we go. And all of this again over a squared h times a plus h squared. Oh, I keep putting it in the wrong spot. And my numerator, notice my a squareds are canceling out. So my numerator is minus 2ah minus h squared. And now we see this common factor of h everywhere, which is good, because at some point we want to substitute h with 0. And so notice at this point, every single term has a factor of h. It's a little more obvious if I literally take out a factor of h from the numerator and the denominator. So I'm going to take a factor of h out of the numerator, so I get negative 2a minus h. And I already have this factor of h in the denominator. So I can see how these cancel out. And so now I have an expression that I can actually evaluate by substituting h with 0. So notice if I look at this now, there is nothing stopping me. I'm not to actually substitute h with 0. So let me now evaluate the limit as h approaches 0. So negative 2a minus 0 over a squared times a plus 0 squared. Well, it's kind of silly keeping those zeros. And then what I get is negative 2a over a to the power 4, which simplifies to negative 2 over a cubed. And there's my derivative at a. And so if I look back at this function, if I wanted to find the slope at any given point, I don't know, right there at 3, I just substitute a with 3. Negative 2 over 3 to the power of 3. So negative 2 over 27 is the slope at that point right there. And notice the only point I can't actually find the slope of a function for this particular function is at 0, because there's a vertical asymptote there. And notice my derivative, if I replace a with 0, I'm dividing by 0. Now again, like I mentioned last day, yes, this is a fair amount of algebraic work. And yes, eventually we will learn ways to speed this up. But once we do that, our algebraic work will actually get more complex, because we can do far, far, far more complex functions. So again, yes, it's a bit time consuming, but let's not be in a rush to get ahead of ourselves too quickly. Okay, this is one of the fundamental ideas we want to have down. And again, working with limits is really what this current unit is about. But with that said, I'm done this. So we're going to see lots more with derivatives kind of for the rest of the course. But for now, I'm done.